Hi, everybody. Welcome to our first online lecture. Um, we're going to be doing a few of these over the next, week or so. We're going to start our next chapter on work and energy. So I have posted the note packet for you, the blank PDF, and I'll be kind of working through a couple pages a day. So the plan today is to do pages 3 and 4 in the notes. Page 2 is blank. And then do page 5 and 6 on Monday. Have you guys work through a problem set on Tuesday. Do pages 7 and 8 on Thursday, and then another problem set on Friday. All right. So without further ado, let's go ahead and get into it. We've got our little comic here, and it's Garfield that says, I'm going to take an active part in energy conservation. And then he is just taking a nap, which many of you can probably relate, as your pets are probably sleeping all day like mine is. So this idea of conservation of energy is going to be something that we talk about. It maybe is something that you've heard as like a law of physics, is that energy cannot be created or destroyed, that energy is always conserved. And that's going to be something that we get into in this chapter. Before we do that, we have to kind of define what is energy, what are some different types of energy, and then we'll get into how is energy conserved, how is energy transferred. So we're going to be talking about all of that different things, and it's really a different way of looking at physics. So far we've been kind of looking at forces, we've been talking about kinematics, and energy is kind of a different way of approaching a lot of the same problems. So yeah, without further ado, let's go ahead and get into it. So I'm going down to page 3 here. And what we want to talk about here is basically, this is what I was just saying. We've been discussing motion in terms of forces and accelerations and things like that. And instead of focusing on these forces causing acceleration, we're going to be focusing on something else. And so here we have, the summary statement of kind of what we've studied so far. An object accelerates from rest to some final speed, which we called, final velocity or VF, after moving through some distance. This was all kinematics. This occurs because a force caused its speed to change by pushing or pulling on the object. So in summary of what we've done so far, we have that, use green here, that forces cause acceleration, which will change an object's speed. Right? And that's what we've got so far. Right? Now, what we're going to do now is we're going to talk about things in terms of energy. Um, and it's the same thing, but what we're going to phrase it a little bit different. Instead of forces causing acceleration, what we're going to say is that forces do something called work. And you looked at that in the POGL the last 2 days, that forces do work, which will change an object's energy. And so instead of thinking about it in terms of speed, acceleration, and changing an object's velocity, we're looking at it in terms of forces doing work, changing an object's energy. So it's a little bit of a shift in how we're going to be thinking about this. So let's define what is work, this new concept that we have here. The basic definition for work is a force causing a change in an object's kinetic energy, which we will, from this point forward, write as Ke. So a force causing a change in an object's kinetic energy after an object moves a distance, which we'll say d. All right, so basically the force is going to move the object. That's what forces do. They cause accelerations. When that object moves, it has kinetic energy and is causing the object's kinetic energy to change. If the object was at rest initially and then has a final kinetic energy, it's gained kinetic energy. If it's a force like friction that's working to slow the object down, then it's taking away the object's kinetic energy. And this gets into our discussion of positive versus negative work. So you can have you can still have positive and negative work, but work is a scalar. So it is just a number. There's no direction with it, but you can have positive and negative work. Right? So work is a scalar, not a vector. But we can have positive and negative work. So positive work versus negative work. So positive work means that we will increase the kinetic energy. And negative work means we will decrease the kinetic energy. And when we have an increase in kinetic energy, this means that the object will speed up. Velocity will increase in magnitude. And when we decrease, this means that the object will slow down. All right, and then finally, we'll have this, this work equation here. And this is defined as work equals force. It's actually it's force with a dot product. So it's actually this force dot product distance. But the way we can write this in terms of solvable. So if you later study vector mathematics, you'll learn about dot products, and maybe you have learned about dot products and their definition. But work is a dot product of f and d, which returns a scalar value. That's why work is a scalar, not a vector. But the equation we're going to use is that work is going to be defined as the magnitude of f times the magnitude of d, or the distance, times cosine of the angle between those objects. So theta here is the angle between the vectors f and d. Okay. We have energy for work, or units for work. So our units are going to be something referred to as a joule. Which we'll use the abbreviation J for. All right. I think that's it for this page. So let's move on to some examples of how we might use this equation, how we can calculate work. So on page 4, I've got a couple examples, and we will kind of go through what does that force distance equation look like. All right. How are we doing on time? Pretty good so far. All right. So the first example says, what is the work done by the force shown below? Which component X or Y of the force is the piece which actually does the work, causing the box to move? So we have a force vector here of 10 newtons, and it's up at an angle of 35 degrees. So again, this is our, like we could write this force vector as, F equals 10 newtons at 35 degrees, vector notation, right? And as you recall, when we have a vector at an angle, we can break it into its components. So I'm gonna go ahead and write its components with green and blue here. So if we were to, do our right triangle like we've done before, we have, this is our, let me redraw that was bad. So our x component will go right here. So this is our force x. And our y component will go right here. And these two components we can solve for with our cosine of 34. So, cosine of 35 times our magnitude. So we've actually done this many times. We can write Fy as 10 sine 35 degrees, in the y-hat direction. We can do Fx as 10 cosine 35 in the x direction, right? So we have these two values here. Now, if we think about this in terms of components, and then back to our work equation, which we wrote on the last page, which I'm going to rewrite here, work equals F d cosine of theta. Now, there's two ways to think about this. We can think about this as the whole, where we look at the vector F and we look at the vector delta x, which is going to be representative of our distance vector. Displacement here was 25 meters, and it's going to the right. So we can look at it just in terms of that, and there's kind of two ways to plug this in. So the first way is really simple. All we do is we just say, work equals, and then the force here is 10 newtons. The distance traveled was 25 meters, and the angle between force and delta x is 35 degrees. So cosine 35 degrees. Plug that all in, make sure your calculator is in degree mode. And then you'll get the answer of 204.8. So we could say about 205 joules. All right, and that's all the simpler it has to be. Now there's an alternative way of doing this, which I do want to show you, which is in terms of its components. So the other way we can think about this is we can look at the amount of work that each component does. So I can look at the y component first, and I can say the work done by the y component. I'm just going to call this work of y, or of Fy, of my y component here, is the value of that force y times distance times the angle between my force y and my displacement. And if I think about my force y is going straight up and my displacement is going to the right, and so these are at a 90-degree angle, they're perpendicular. So that's the theta is going to be 90 degrees. And if you recall, the work done, or sorry, if you recall, cosine 90 is 0, which would make this whole thing equal to 0. So the work done by force of y is 0 joules. And so this force in the y direction is not doing any of the work. So if we look at answer this question, which component of the force is the piece which actually does the work, the y component is not helping to move the box. It's not moving it at all to the right. It's just trying to lift it off the ground, but gravity is holding it on the ground, so it's not doing anything. But if we look at the x component here, then now I see something interesting happening. So the work force of x equals Fx, distance cosine of theta, and this time this is the angle between Fx and delta x. And so in this case, Fx is this way and delta x is this way, and so my theta is going to be 0 degrees. And cosine of 0 is 1. And so what I end up getting is I get my x component, which is 10 cosine 35, my distance, which is still 25, and then cosine of 0. Because this is the angle between these two vectors, Fx and distance, whereas here, the angle between Fy and distance was 90 degrees. And then in this one, we looked at it in terms of just the two vectors, where we looked at the whole component F, and we looked at this vector distance, and that's why we used the angle of 35 in this one. All right, so we get 3 different angle values for depending on which force we're looking at. But you'll see the math actually is going to be the same here. If I look at this, it's 10 times cosine of 35 times 25 times 1. This is 1 when you plug that in. So this term goes away, and then it's just a matter of multiplying these 3 together, and you're going to actually see that you get the same answer as you did for when you looked at the whole thing, 205 joules. And this is interesting because now I know, all right, the x component is the one that does all the work. The y component is contributing none of the work. It's not changing the object's kinetic energy. Only the force in the x direction is changing the kinetic energy. So if we looked at, to answer this component, which component x or y is actually causing it, we would say the x component actually is doing all the work. All right, and then I got one more example for us today, and then we'll wrap things up. All right, so example 2 here says find the work done by each of the 4 forces shown below. We have force 1, 2, 3, and 4. We're ignoring gravity and normal force here. And the reason we can ignore those forces in this case is simply because this thing's moving to the right. That's its x direction. And so those 2 forces, gravity and normal force, we don't really have to, account for them, right? They're in the, oops, ooh, bad. They're in this problem as, this would be force normal, this would be force gravity, but because they're both at 90-degree angles here and here, they do 0 work. And so we're not going to take those into account in this case. We're going to ignore those, and we're going to pretend that we have 4 ropes or something attached to this object, and they're all pulling on this object in 4 different ways. And we're going to try and figure out which way does this object go based on these, and you should kind of be able to tell here we have a 6 Newton force and a 5 Newton force pulling to the right, and only a 2 Newton and 2 Newton force pulling to the left, so it's going to go to the right. And then it tells us that it goes 40 meters to the right, and we're trying to find the work of each of these plus the work of the total work, so all 4 combined. Right. And so what you want to do for this problem is kind of break each vector and treat each vector as its own amount of work. So if I look at just force 1 here, and this is my distance vector here, the angle between we'll write all the angles out. So theta 1, I'm just going to label these as theta 1, theta 2, theta 3, and theta 4. Theta 1 is going to be 0 degrees. So there's no angle between force and distance. Theta 2, for force 2, is going to be 50 degrees. Theta 3 is this angle here, which goes all the way around. Now this is a 20-degree angle here. And so this would be 180 minus 20. Or 160 degrees. And then finally, theta 4 would be just 180 degrees, complete opposite direction. Okay, so we always are finding the angle between the 2 vectors. So that's our first part. We've got our theta values, and we have our force values, and we have our distance value is 40 for each of these. This is kind of like OCD here, bothering me. I'm gonna use a different color for each one. Theta 1 equals 0 degrees. All right. So each one has its own angle, each one has its own force value, and they're all using the same distance value. So now it's just plug and chug into our formula, starting with work done by object or by force 1 on the object is force 1 distance cosine theta 1, and so this will be force 1, which is 5 newtons, and the theta and the theta of 0. So this will be 5 times 40 cosine of 0. Cosine of 0 is 1, which just means that I get 200 joules of work by the first object. For the second object, F2 distance cosine theta 2. So F2 is 6 newtons of force. The object's still moving 40, but now my angle is cosine of 50. And if I plug this in, I actually get, let's see, 154. 0.3 joules. And this is interesting as a result, right? We have 6 newtons is a larger force than 5 newtons, but the 5 Newton force is actually doing more work because it's in the x direction entirely, whereas the 6 Newton force is only 50 degrees, or is at 50 degrees, so less of it is in that direction. And you can actually see, if you project this vector down along the x-axis here, you can see it's not quite as long. Now, I don't know if this is drawn to scale or not, but it's a little bit less than that vector. So less of it's contributing to actually doing the work there. Now for theta 3, which is this vector here, we would have same idea, cosine of theta 3, force of 2, distance of 40, and cosine of 160. And this would get you a negative answer, negative 75.2 joules, which means this actually is working to slow the object down. These two are working to speed the object up. This force is working to slow the object down. And same thing for work 4. Two times 40 cosine of 180. Cosine of 180 is negative 1, so this would give us negative 80 joules. All right, and that's what we have so far. All right, so that is part A. Find the work done by each of the forces shown below. So we got that done. Indicate whether that force will cause the box to speed up or slow down. So let's just do that right here for part B. So force 1 is going to cause it to speed up because it's positive. So it's going to cause it to speed up in that direction. Force 2 is also going to cause it to speed up. Force 3, which is going to the left because it's doing negative work, will cause it to slow down. And force 4, which will also cause it to slow down. All right, so that's part B. We can check that one off. And then finally, find the net work. So we haven't talked about this concept yet, but we've talked about net force. And net force was the total force. Net work is the same thing. It's the total work done on the box by all the forces acting on the box. So in part C, all we have to do is add up each of the works. So the net work is going to be work 1 plus work 2 plus work 3 plus work 4. And this will give us a total value, net work, equals 200 plus 154 minus 75.2 minus 80. It gives a value of approximately 199. We round it. So about 200 joules of work. And basically you can see, this is minus 155 and that's plus 154. So we get a minus 1 net from that 200. And so we know that the object will speed up overall, and it will speed up to the right. All right. So thanks for watching the video today, guys. Go through it, fill it. Hopefully if you have any questions, please feel free to ask me. And we will be going through pages 5 and 6 on Monday. So have a good weekend, and we'll talk to you then.